Hello all, today we will see the object query language OQL. That is a query language proposed for ODMG object model, and it is designed to work closely with the programming languages for which ODMG binding is defined, such as the C++, Smalltalk and Java. An OQL query embedded into one of these programming languages can return objects that match the type system of that language. Additionally, the implementation of class operations in an ODMG schema can have their code written in these programming languages. And the OQL syntax for queries is similar to the syntax of the relational standard query language SQL, with additional features for ODMG, that is concepts such as object identity, then complex objects, operations, inheritance, polymorphism and relationships. And simple OQL queries, the basic OQL query syntax is a select from where structure, as it is for SQL. For example, the query to retrieve the names of all departments in the College of Engineering can be written as follows. Okay, to retrieve the names of all departments in the College of Engineering. So that is select D dot name from D in departments where D dot college is equal to engineering. And in general, an entry point to the database is needed for each query, which can be any named persistent object. Okay, for many queries, the entry points is the name of the extent of a class. That is, the extent name is considered to be the name of a persistent object whose type is a collection, in most cases a set of objects from the class. Okay. So we need to give an entry point, and that will be always a named persistent object, which means that is an extent, because extent name itself is name of a persistent object. For example, the named object departments is of the type set department, persons is of type set person, faculty is of type set faculty, and so on. We can define it like this. And use of an extent name, that is departments in the previous query, as an entry point refers to a persistent collection of objects. So whenever a collection is referenced in an OQL query, we can define this iterator variable. Okay, that ranges over each object in the collection, and iterator D in the previous example serve as an iterator and ranges over each object in the collection based on the conditions specified in the where clause. And in the a previous query, only persistent objects D in the collection of departments that satisfy the condition D dot college equal to engineering are selected for the query result. For each selected object D, the value of D dot D name is retrieved in the query result. Hence, type of the result for this previous query is bag of string. Okay, because the type of each D name value is string, even though the actual result is a set, because D name is a key attribute. So different syntactical options for this specifying an attribute, iterator are D in departments or departments D, or departments as D. All these are possible syntax. Then this database as query results and type, data type of this query results. The result of a query can be of any type that can be expressed in the ODMG object model. A query does not have to follow the select from where format. In the simplest case, any persistent name on its own is a query whose result is a reference to that persistent object. For example, the query one, departments. Okay. So this returns a reference to the collection of all persistent department objects whose type is set department. Similarly, suppose we have a persistent name CS underscore department to a single department object, the computer science department. Then the query CS underscore department that returns a reference to that individual object of type department. And once an entry point is specified, the concept of a path expression can be used to specify a path to return attributes and objects. So a path expression typically starts at a persistent object name or at a variable that ranges over individual objects in a collection. This name will be followed by 0 or more relationships name or attribute names connected using the dot notation. For example, suppose we have departments dot chair, or we have CS department dot chair dot rank, or CS department dot has faculty. So this will, for example, departments dot chair, and that runs object of type faculty because that is the type of the attribute chair of the department class. Okay, this will be a reference to the faculty object that is related to the department object whose persistent name is CS underscore department via the attribute chair. That is reference to the faculty object who is chairperson of the computer science department. Okay, exit. Then views as named objects. The view mechanism in OQL uses the concept of a named query. So the define keyword is used to specify an identifier of a named query, which must be a unique name among all named objects, data names, method names, function names in the schema. If the identifier has the name, has the same name as an existing named query, then the new definition replaces the previous definition. Once defined, a query definition is persistent until deleted or redefined. That is, a new definition comes. A view can have parameters in its definition. It can include parameters in its definition. A definition of an OQL view, a view to include students in a department who have minor. So it defines a named query that is has minors to retrieve the set of objects for students minoring in a given department. So minoring in a given department, this is department underscore name. And now we can use this has underscore minor in queries. So that is, we will be able to write it like has minors of computer science, for example, which would return a bag of students minoring in the computer science department. Okay. So we can define a view like has minor in some particular department. Okay. So it will select student details who has minor in some particular department. So now we can use has minor in queries. For example, has minor of computer science. It will return bag of students minoring in the computer science department. And single elements from single collections. An OQL query will return a collection as its result, just as a bag, set, or list. Okay. If the user requires that a query only return a single element. Okay. If the query only returns a single element, there is an element operator in OQL that is guaranteed to return a single element E from a singleton collection C that contains only one element. If C contains more than one element, or if C is empty, then the element operator raises an exception. For example, this query select, that is element select D from D in departments where D dot name is equal to software engineering. Since a department name is unique across all departments, the result should be one department. The type of the result is D dot department. So this returns a single object reference to the software engineering department. Okay. And collection operators. So because we have query expression specify collections as their result, a number of operations has been defined that are applied to such collections. These include aggregate operators as well as membership, quantification, that is universal and existential. Then these can be applied over a collection. Okay. So the aggregate operators, the examples are min, max, count, sum, average. These operate over a collection. And the operator count returns an integer type, and the remaining operators, that is max, count, average, sum, all this return the same type as the type of the operand collection. So for example, compute the average GPA of all seniors majoring in business. So we have average, select S dot GPA from S in students, where S dot class equal to senior and S dot majors in dot D name is equal to business. Okay, so this will compute average GPA of all seniors majoring in business department. And the membership and quantification expressions return a Boolean type. Okay, that is true or false. For example, we have these operations E in C that returns true if E is in the collection C, and for all E in C, then B. Okay, colon B. That this actually returns true if all the elements of collection C satisfies this condition. Okay, and X is E in C colon B. That returns true if there is at least one element in C satisfying this condition B. Suppose we want to retrieve the names of all students who completed the course called CS 101. Okay. So here we have a nested query that returns collection of course names that each student S has completed course names, and the membership condition returns true if this CS 101 is in the collection for a particular student. Okay, so that is select S dot name, then S dot name dot F name, S dot name dot L name, then S in student CS 101 in, where we'll return all the courses that each student has completed, and if it is the this CS 101 is there, then that names of that students will be returned, F name and L name will be returned. Then we have ordered collections. Collections that are lists and arrays have additional operations such as retrieving the ith, first and last elements. For example, these are additional operations. Additionally, operations is for extracting a sub-collection and concatenating two lists. All these are additional operations for this list. So hence, this query expressions that involve lists or arrays can invoke these operations. Okay. Example of an ordered operation. So to retrieve the last name of a faculty member who earns the highest salary. So first select faculty, that is a structure faculty F dot name dot last name, salary F dot salary, from F in faculty ordered by F dot salary in descending order. So here we have the first operator on a list collection that contains the salaries of faculty members sorted in descending order by salary. Okay. Thus, the first element in this sorted list contains the faculty member with the highest salary. So this query assumes that only one faculty member earns the maximum salary. So this will return the first name of the faculty who has the highest salary. The salary is sorted in descending order, and the first person will be taken out. Okay. The grouping operator, the group by clause in OQL, although similar to the corresponding clause in SQL, provides explicit reference to the collection of objects within each group or partition. So we can see an example to retrieve average GPA of majors in each department having greater than 100 majors. So select department name, average GPA, average select, then GPA from P in partition from S in students, group by department name, S dot majors underscore in dot D name, having count partition greater than 100. So having close can be used to filter the partition sets. That is, the select only some of the groups based on the group conditions. Here the having clause selects only those partitions or groups that have more than 100 elements. Okay, if this particular partition or group has more than 100 elements, only those will be selected. That is, departments with more than 100 majors. So this will also return the average GPA of the students. So it will return the average GPA of majors in each department having more than 100 majors. So if it has more than 100 students, then this will be this average GPA will be computed. Then this C++ language binding in ODMG standard. So the C++ language binding specifies how ODL constructs are mapped to C++ statements or C++ constructs. This is done via a C++ class library that provides classes and operations that implement the ODL constructs. An object manipulation language, that is OML, is needed to specify how database objects are retrieved and manipulated within a C++ program. And this is based on the C++ programming language syntax and semantics. So in addition to the ODL, OML bindings, a set of constructs called physical pragmas are defined to allow the programmer some control over the physical storage issues, such as the clustering of objects, utilizing indexes and memory management, etc. The class library added to C++ for the ODMG standard uses the prefix D underscore for class declarations that deal with database concepts. The goal is that the programmer should think that only one language is being used, not two separate languages. And for the programmer to refer to database objects in a program, a class D underscore ref of T is defined for each database class T in the schema. Hence, a programmer variable of type D underscore ref T can refer to both persistent and transient objects of class T. So in order to utilize various build types in the ODMG data model, such as collection types, various template classes are specified in the library. So for example, we have an abstract class D underscore object T specifies the operations to be inherited by all objects. Okay, that is an example. Or an abstract class D underscore collection T that specifies the operations of collections. And remember that these classes are not instantiable, but only specify the operations that can be inherited by all objects. Okay, all objects or all by all collection objects. And we have a template class, and that is specified for each type of collection, ODMT collection. These include D underscore set T or D underscore list T, D underscore bag T, D underscore warranty T, D underscore dictionary T, D underscore VRA T, and they correspond to the collection types in the object model. Okay. So the programmer can create classes of types such as D underscore set, D underscore ref student, whose instances would be sets of references to the student object. Okay, so suppose programmer writes like this: D underscore set, then D underscore ref student. It means that whose instances would be sets of references to the student objects. And data types of attributes. So the C++ ODL allows a user to specify the classes of a database schema using the constructs of C++ as well as the constructs provided by the object database library. For specifying the data types of attributes, the basic types such as D underscore short, that is short integer, or D underscore U short, unsigned short integer, or D underscore long, that means long integer, and D underscore float, that is floating point number, are provided. And in addition to the basic data types, several structured literal types are provided to correspond to structured literal types of the ODMG database object model, and they include D underscore date or D underscore time, D underscore interval, etc. So next is to specify relationships. The keyword rel, relationship rel, is used within the prefix of type names. For example, by writing D underscore rel underscore ref department has majors, then minus dot in the student class, so which means we are defining this majors in and has majors are relationship properties that are inverses of one another and hence represent a 1:n relationship, binary relationship between the student and department. And for this OML, object manipulation language, the binding overloads the operation new so that it can be used to create either persistent or transient objects. To create this persistent objects, one must provide the database name and persistent name of the object. For example, by writing D underscore ref student s equal to new name, new within parenthesis, suppose db1 John Smith student. Okay, the programmer creates a named persistent object of the type student in database db1 with persistent name, this John Smith. And C++ also binding also allows the creation of extents via using the library class d underscore extend. Okay. For example, we have d underscore extend person, all persons of CS 101. So the programmer would create a named collection object all persons whose type would be d underscore set person, and in the database or in the CS101 that would hold persistent objects of type person. Key constraints are not supported in the C++ binding, and any key checks must be programmed in the class methods. And also the C++ binding does not support persistence via reachability. The object must be statically declared to be persistent at the time it is created. The relationships are handled by reference attributes that include OIDs of related objects, and single and collection of references are allowed. References for binary relationships can be expressed in single direction or both directions via inverse operator. And relationship among tuples are specified by attributes with matching values, that is via foreign keys. And we have foreign keys are single valued. Then M2N relationships must be presented via a separate relation, that is a table. So this is the relationship ODB versus RDB. Relationships are handled by reference attributes that include OIDs of related objects. Single and collection of references are allowed. And inheritance relationship in ODB versus RDB. Inheritance structures are built in ODB and achieved via this colon and extends operators. Okay, RDB has no built-in support for inheritance relationships. There are several options for mapping inheritance relationships in RDB. You can see them in chapter 7. Another major difference between ODB and RDB is the specification of operations. So in ODB, operations specified during design, that is as part of class specification itself. RDB means operation specification may be delayed until implementation. That is the case with RDB. So these are some difference between this ODB and RDB. So thank you.